look at my notes real quick just to double check. But when we last spoke, all I had gotten to was how to decompose a vector. I had talked about how to add vectors graphically, so that's something you still need to be able to do. I also talked about how to add vector or subtract vectors graphically. You need to be able to do that. And remember, there's two different ways. You have to be able to add two vectors that I've drawn, and I can draw those two vectors tail to tail, or I can draw those two vectors head to tail. And then in both of those cases, you should be able to draw right on that diagram exactly how the A plus B looks in both cases. Okay, that means not only do you have a line, but you have a line with a head on the end, and the head's pointing the right way. Okay, so you got to be able to do that with two vectors that are head to head, or excuse me, head to tail, and you got to do that with two vectors that are tail to tail. Then you also need to be able to find A minus B again with A and B head to tail and with A and B tail to tail. So make sure y'all can do that. We went over that last time. All I really have left really is to show you how to actually add vectors, and I'm going to attempt to do that today. So let me go ahead and show you some stuff about vectors. So I'm going to start by sharing my screen. It's my iPad screen. Actually, before I do that, does anybody have any questions that they need me to answer before we get started? So that could be stuff from previous chapters, stuff about the syllabus. Remember, y'all do have a test that's due this Sunday at our, yeah, for you guys, it's Sunday at 11:59 p.m. That's the first online test. The word is that I am planning on pushing the other face-to-face and online tests back 1 week, except for maybe the last two or three. They might not be, but when I decide exactly how I'm going to do that, I'm going to update the syllabus and post a new version of the syllabus. The new version will have a date on the end of the file name, and that date will obviously be like February 5th or something like that. So that's how you'll know it's the more precise one or the better one. So anybody have any questions on any past material, syllabus stuff or whatever?
I had a quick question, but it was about the lab.
Uh-huh.
I saw that the labs got graded today. Um, but
Yes, I actually got a little discombobulated, but yes, they did get graded today. But the problem was a lot of people didn't follow my instructions on the videos, which was that you're only supposed to turn your labs in the lab section, not the
well,
lecture section. So if you go and turn it in there, I can go ahead and finish it.
I wanted to point out, and when you go to the grades, if
Mhm.
anyone else doesn't see this, please correct me if I'm wrong. But
Right.
there's two submissions for Lab One Intro to Lab.
Yes,
Um,
I replied to that on your. I think you were the one that might have said that to me on
oh no,
in the turn in? Okay. Someone did. I don't know who that was, but go ahead.
oh yeah. So I just if I turned it into the other one, would you like me to just turn it into the
If you
second
could,
one?
that would be great. It's my,
Okay.
I mean, I will find it if it's turned in the L02 course. If it's in the D01 course, that's where I need you to put it in the, or excuse me, in the N02B course. If it's in there, then yeah, put it in the L02. And if there's two of them that say, Intro to Lab, uh, put it in. If you put it in one, put it in the other just to be sure. And if you don't, I'll still have to find it. But today I was only able to find three of them. And then I remembered which lecture section was corresponded to that lab. And then I discovered there was a lot more on there. So I will be doing that tomorrow. Uh, so just be advised that that lab will be graded and you'll have it graded tomorrow. You'll definitely have it graded by the weekend, but I suspect I'll do it tomorrow.
Okay. Great. Thank you.
Yeah, thanks for that, Brianna. Yeah, so the whole semester, make sure you only turn your labs in at the lab Canvas course. And yeah, I know it actually shows up on our lecture course. It's not supposed to, but when you copy things over from other courses, it sort of, you have a choice of selecting each individual item or selecting a whole swath. It's too time consuming to select individual items, so I had to do a swath, and that meant that stuff was in there, and then I have to go down and turn them off. So it's probably no saving of time by me doing the swath. So next time I'll do that, but you will have a bunch of labs turn-in spots on the lecture course. I'm going to try to dismantle those as soon as I see them, but they're not supposed to go there. So please bear with me, and I thank you for pointing that out to me because yeah, that's definitely a problem. Anybody else have any questions?
Yeah, I turned it into the lab section of
Okay.
Canvas, but it appeared that you didn't see it. Is there like another place?
There might have been. That's what Brianna was talking about. So if you look in, I don't know. Various people go to various different places, but the intro to lab, the turn-in that I meant for it to be, was right there in week one's module. And just make sure you're in the L02 lab, not the one right now that says N02B at the top.
Well, that's what I thought was strange because I turned it in personally through the
Uh-huh.
in the modules, the week one, and that assignment. But it seems like there was two of that assignment in the LO2B grade book. So I'm just gonna go through the grade book to turn in the other one.
I'm actually pulling that up right now to double check and see exactly what happened for Daniel as well. I thought I did grade a person by the name of Daniels, uh, but it might have been a Daniela or something. But I did remember doing something. So let me check what's happening here. I'm
I
looking at
turned
our.
it in through the module. But like she was saying, if you go through grades, then
Mhm.
there's two listings, but I
Ah,
turned it
okay.
into the module where there's only one. I didn't realize that I needed to go through the grade book.
You shouldn't have to. That's not your problem. It would help me if you put it in both of them just for right now. But that's not your job. You're not supposed to do that. That's just me having issues and that I need to fix. I do see Brianna's already been turned in here. Oh yeah, Daniel, you were one of them that didn't have that, so I apologize. I'm looking for it again.
I had that same issue actually. I turned mine in, and there are two spots for that intro to lab.
Oh, I see. I just found another one. Yep. Oh, yep. There it is. Holy crap. What are the odds? The one that that was in my module only had three, and the one that's not in my module has all but three. So I now have all of them. Y'all don't have to do anything. I can find this. Okay.
Yay! Thank
Yeah,
you.
they're there. I'm sorry about that, folks.
No, I'm glad we cleared it up.
Yeah, it's much better to have it cleared up either way. So, anyways, I'm killing one dragon at a time, I guess. All right, so let's get started on this vector addition thing. So what I try to tell you guys is when you go to add vectors, there's very specific quote unquote formulas that could be used. I never ever thought in terms of formulas. So I would hope you all can come to that same place, but you might not be there yet. So it's perfectly fine to, use tables to add integrals. That's something we teach in our 201, 202 sequence. It's not what we normally teach in our 241, 242 sequence, but you certainly are capable of using it. It just takes more time to draw a table and that sort of stuff. But the fundamental idea is this. A vector can be it's an object that's in space, and what we're dealing with now are vectors in space. There's something else we're going to be covering, probably not this semester, but definitely next semester, called vector fields and scalar fields and that sort of thing. With vector fields, all bets are off because basically, with a vector field, you have a specific vector assigned to each point in space. So here's a vector. All right, here's another point in space. There's another vector there. Here's another point in space. There's another vector there. That's different. We're talking about just vectors in the space right now, and that's what we're doing pretty much all of this first semester. And the what you know so far is that vectors have direction and magnitude. So you could pick up vectors and move them about in space, and as long as you don't stretch them, which would change their length, or compress them, which would change their length, therefore changing their magnitude, or twist them, which would change their direction. As long as you don't do those two things, uh, changing their lengths or changing their direction, then you're free to move them around. Okay, so that's the key thing to understand. Because of that, you have then vectors that you can move all around, and that'll come in handy when we start to add and subtract vectors, like I showed you last time with adding vectors graphically and then with subtracting vectors graphically. So you definitely want to be able to do that. But now we're going to talk about doing it mathematically as opposed to graphically. And when you have a vector, it exists in space, and then you might have to make a coordinate system for it to make sense. Uh, that coordinate system, if it's in 2 dimensions, is great. That means you only have an x-axis and a y-axis. If it's in 3 dimensions, then you have an x-axis, a y-axis, and a z-axis, and they're all perpendicular. I don't know why I keep yawning, but it's killing me. So, with this in mind, what you have to do in order to add vectors is you take your vectors mathematically and you're going to resolve them into components. That means that each vector will have an x component and a y component, or if we're doing 3 dimensions, then each vector will have an x component, a y component, and a z component. And once you break those vectors down into those components, then like components add. So you can take the x component of one vector and add it to the x component of another vector and another vector and another vector. And when you're done, when you've added all the x components together, what you have is the sum of the x components, which is called the resultant x component. So it's the x component of the sum. Then you do the same thing with the y's, and you'll have a resultant y component. And of course, if you have z's, you got to do the same thing. Now, what that is in terms of formulas is this. So r, the vector, is, let's say, equal to a plus b. And you can do other vectors too, so I'll just put plus, 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 dot, dot, dot. So for any number of vectors, this is going to be true. One thing you can say is that vector A is equal to the x component of A times this neat little unit vector that we invented just to make things a little easier. So if you imagine a vector that's 1 unit long, remember we can picture vectors as just arrows. So we're imagining an arrow that is 1 unit long, 1 unit, not 1 meter, not 1 foot, not 1 inch, not 1 Newton. Okay, it's 1 unit, and it points in the positive x direction. That's the I hat vector, and the hat indicates that it's a unit vector. Some people also call this the x hat vector, so you could write it as ax x hat. If you only have y components and x components, then this whole vector A would be basically this. So there's another vector that points in the positive y direction that has a length of exactly 1 unit. That vector is called j hat or y hat. So I could also write this as ax x hat plus ay y hat. That would be acceptable as well. And then there's yet another way that saves you a lot of time. And in that case, it would be a sub x, comma, a sub y. Notice it sort of looks like the notation that we use for points, but with points, we use a left parenthesis on the left-hand side, a right parenthesis on the right-hand side. Here, we use a less than symbol on the left-hand side and a greater than symbol on the right-hand side. Oh, God, I can't stop yawning. I'm so sorry. All right. Similarly, we can define B as, in that shortcut way, I'm going to say BX, BY, like that. Okay. Now that we have that, we have some idea how we write our vectors. So ultimately, what we get is Rx, the x component of the resultant vector, is AX plus BX plus all the other x components that you have for each of the vectors. Okay. Then Ry is equal to AY plus BY plus dot, dot, dot again. You're supposed to put 3 dots, by the way, and those 3 dots are called an ellipses, Ellipses. Might be a single L, but I'm pretty confident it's 2 L's. Okay. And then, of course, your resultant vector could be written as R is equal to Rx I hat plus RY J hat. And of course, if you had a Z component, you could add that and you could add another equation. So that's really what the quote unquote equations for adding vectors are. But I think that should just make perfect sense to you because they're like components. You can imagine this as being a AX next to a I hat. And in terms of algebra, that looks like I can only add things that are terms in I hat, just like I can only add 2x squared to, 0.5x squared. I can't add 2x squared to 1x because x squared is a different term than x to the first power. So the same thing's happening with that. So hopefully that makes a little sense. Now, what I want to do is I want to give you an example of a vector problem. And I want to do this in terms of three special triangles, not because I need you to do these special triangles, but because it's going to save me time to do examples where I don't have to take time to calculate, the sine of an angle or the cosine of an angle or the tangent of an angle. So the special triangles are, for one case, I have the 3, 4, 5 triangle. So this is length 4. This is length 3, and this is length 5, and this angle up here is 53.13 degrees. That's not a very good way of writing it. I'm going to move it and put it somewhere else. I'll just say this angle is 53.13 degrees. This angle, of course, is 36.87 degrees. And that's one triangle that we have, and that's called the 345 triangle. There's another triangle we have, and this one is the 45-45-90 triangle. So in this case, you have this angle right here is 45 degrees. This angle is also 45 degrees. This side is 1, this side is 1, and obviously the Pythagorean theorem would tell you that this side is the square root of 2, which is approximately equal to 1.414. Okay? Now, there's another triangle that we could do, and I'm going to write it like this. So this side will be side 1, and this side will be a side whose length is the square root of 3, and that is approximately equal to 1.732. Now, the hypotenuse of this triangle is in fact just 2, and this angle is 60 degrees, and this angle is 30 degrees. Notice, in case you've never had a geometry course, one of the things you learn in geometry is in a triangle, the angle with the largest angle is opposite the largest side. Now, in all of these, the right angle you often have probably seen written with this little box in the side. If you think about that little box as looking like an arrowhead, then that gives you the added comfort of knowing, oh, the arrowhead points to the hypotenuse, which is the longest side. So the hypotenuse now, this is a problem. I really want to put a E somewhere after this N, and I'm not certain that it's in there. So there's probably a good chance that there's a misspelled word there. But the hypotenuse is the longest side, and it is opposite the 90-degree angle. Okay, so remember that's the one that looks like it has an arrow pointing to it. Like that. Okay, now additionally, if we just randomly draw a triangle, we can call this angle theta, and then this is our right triangle. Notice I'm sticking mostly to right triangles. In principle, you can do non-right triangles, But then you'd have to use the law of sines and the law of cosines. When we get to dot products, I'll show you a little bit more about that so you can be a little bit more confident with using the laws of sines and cosines. But right now, we're trying to stick with just, with just right triangles. So what I'm going to do is I want you all to realize that the hypotenuse is a special side and the other two are called legs, and they're a little less special in the sense that they're the smallest of the two. Now, once you eliminate the hypotenuse because you have this little arrow pointing to it, then all you have left is the adjacent side, which means the angle touching, or excuse me, the side touching the angle, and you have the opposite side, which means the side that's not touching the angle. Notice the hypotenuse is touching the angle, but that's not one of the sides, that's the hypotenuse. Okay, so I can write this down as that's the adjacent side, and I can write this down as that's the opposite side. Then I have a mnemonic I use, and it's probably not the one you use, but it worked for me, so I'll share it with you. And it's some old horse came a hopping, or maybe hopping through our alley. Okay. Now that also means sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tangent theta is equal to opposite over adjacent. Now, some of you probably know this, and that's so ka toa. Okay. All that also is the same thing as some old horse came a hopping through our alley. So feel free to use that if that's what you are comfortable with. The main thing is it just keeps us honest about knowing what sides are what. So if I were, for instance, to give you a triangle like this, let's say this angle right here is 36.87 degrees, and this triangle is or actually this hypotenuse is a vector, and that vector is called A, and the magnitude, the way I could write magnitude, for instance, is just put an absolute value bar around it, and then the magnitude is going to be, let's say, actually, let's do it a little more crazy. Let's say this magnitude is 25.00 meters. Now, I'm going to add to this and say that this is my x-axis, and this is my y-axis, so that you see that this right here is the origin. Okay? Now, if you imagine the shadow that the x-axis, or excuse me, that the vector A puts on the x-axis, then you know what the length of the x component is. So this is just a shadow right here. Notice it ends directly below the end of the vector. That length, remember, if you write a vector name with a star over it, you're referring to a vector. But if you write a vector name without the vector symbol over it, you're referring to the length of that vector, just like if you put absolute value bars on it. So that length right there is a sub x. Now, if you can sort of imagine horizontal light casting a shadow, then what you discover is this side right here is the shadow on the y-axis, and therefore this distance from here to here is a sub y. So that's what the length of the y component is, and that's what the length of the x component is. Now, to figure out what the actual x component is, we've got to put a vector symbol there as opposed to just a green bar. Now, the idea is if you actually make a vector out of two component vectors, then they should add head to tail such that you get from the tail of the vector to the head of the vector. So we're trying to go from the tail of the A vector, which mind you is right there at the origin. Everybody sees this is the A vector. So if I tried to walk from the tail of the A vector to the head of the A vector along the components, I would have to walk from here going this way and then from here going that way. So that tells me this vector points that way and this vector points that way. Did everybody see that? This vector points this way, that vector points that way. So now I can go ahead and say, I'll go ahead and use my green again. This is the vector a sub x, and this is the vector a sub y. Okay? So when I wrote, for instance, up here, that was like these things. That was just the components. If I took this whole thing right here, that would represent, notice that's ax times I hat. That represents this whole vector, which is from here to here. That's what that is. Similarly, this vector right here is what this is. Does that make sense to everyone? Okay. Now I see that that angle is 36.87, so that makes me immediately think of the 3-4-5 triangle. Okay? And then I realize the hypotenuse is 5, but my vector has a length of 25. What do I have to multiply by 5 to get 25? So if I multiply 5 by 5, then I get 25. But if I do that to that triangle to keep it the size is right, then I have to multiply this one by 5 so it would equal 15, and I have to multiply this one by 5 so that it would equal 20. Does that make sense to everyone? So what we worked out last time was that you could use trig functions to find these components, and I told you don't skip steps. At least while you're starting, you want to go ahead and take your time and write out what the sine of the angle is, and then write out what that ratio equals, and then write out what the cosine of that angle is, and write it equal to the ratio as well using SOHCAHTOA or some old horse came a hopping. So when I go to do this, I write sine 36.87 degrees is equal to, now I remember some old horse, so I look on here and the angle is 36.87. That's this angle right here. And this is the opposite side because this one's touching it and this one's the hypotenuse. So what I have to write now is opposite, which would be AY over hypotenuse, which is just plain A. Remember, I can write it that way, or I can write it with absolute value bars. Now I can also do cosine 36.87 degrees. And in this case, it's going to be adjacent over hypotenuse, so that's A sub X over A. Now from that, I can get that A sub Y is going to be the magnitude of A, which is 25.00 meters, times the sine of 36.87 degrees, and I can find that the a sub x is equal to 25.00 meters times cosine of 36.87 degrees. Okay? Now that's actually how you compute it. Now, if you want to take that and put it in your calculator, that's what you should be doing. I'm using these triangles to help me not have to type stuff out. And ultimately, you might be able to learn how to do it. If you'll notice in your statics books, they use a lot of triangles that are like the 3, 4, 5. There's a bunch of triangles where integers add up, and they're expecting you to use ratios and stuff like that. That's perfectly reasonable, and that's sort of what they expect you to do. They want you to be that fast so you can do vectors without using your calculator. So I'm showing you more or less how you can do it without using your calculator, because I could look at sine 36.87 and I look up here and I see that that is sine is opposite over hypotenuse. So that's 3 divided by 5. And I immediately know that the sine of 36.87 is 0.6. Okay. And then I'd multiply that, of course, by the 25. But I'm not even going to do that, because what I realized is all I had to do to make the 5 into 25 was multiply by 5. So what I'm really getting is the y component is, in fact, the opposite. And if I look at this triangle up here, the opposite is 15. So I'm just going to write this as positive 15. Now, I had to force that sign up there strictly because the arrow told me it pointed positively in the positive y direction. So that's why I put the positive there. Similarly, when I look at AX, I can see that this is the adjacent side, as is this. The adjacent side would normally be the 4, but in this case, it's going to be the 20. So this one's going to be positive again because it points to the right, 20.00 meters. Does that make sense to everyone? Again, you're not necessarily trying to follow how I got the answer without using the calculator. What I want you to do is check your calculator. Take 25.00 and multiply it by the sine of 36.87. Make sure you're in degree mode, of course, and you should get something like 14.998, okay, or 15.004. And similarly, when you do 25 times cosine 36.87, you should get 20, but it might look like 19.996, or it might look like 20.004. Okay. So has everybody been able to confirm that? All right. Now I'm going to use this knowledge and show you how we're going to add 4 vectors. Okay. And I'm making them special vectors. So you'll notice I called the vector addition problem world's greatest vector problem. It's not. That's sort of me paying homage to the movie Elf, which is one of my favorite movies. I'm a kid at heart, so I love kid movies, and that's sort of a kid and grown up movie. But if you remember, he found the world's greatest coffee. It's me making fun of that. But really what I'm saying here is it's nice because I show you all the different ways I can specify vectors. So now I'm going to explain that to you. So add the 4 vectors. R is equal to A plus B plus C plus D. Okay? So A is going to be a vector that has a length of, let's say, 15.00 meters, and it's going to be at an angle of 36 point, let's actually, no, let's do it 53.18 degrees. So this is one way to specify a vector. I wrote A with an arrow over it. That's how we handwrite a vector. I wrote equals, and then I wrote a magnitude, 15.00 meters with units. And then I wrote at. At is the typical symbol that we use to separate the magnitude from the direction. And then I didn't do anything but say a certain number of degrees. When you do that, what everybody's supposed to understand is that angle 53.18 is measured, since it's positive, it's measured counterclockwise from the positive x-axis towards the y-axis, in other words. Okay, so if you see just an angle with no other clarifying words or anything, then if it's positive, you know you're supposed to go counterclockwise from the positive x-axis that many degrees. If it was negative, you go clockwise from the positive x-axis towards the negative y-axis. Okay, so that's the way we specified A. Now I'm going to do vector B, and vector B, in that case, I'm going to say that it is 20.00 meters. This time I'm going to say it is at, let's say, 30.00 degrees, and I'm going to say it's WON. That means west of north. I'm going to draw a coordinate system in a second to make you understand that, okay? Vector C is going to be 14.14 meters, and this one is going to be at, let's say this one's going to be 45.00 degrees. This time it's going to be south of west. And actually, no, I don't want to use it that way, but this will tell you 45 south of west is actually a good measurement, but I'm going to write it a different way, so that we can use yet another method. I'm going to say, in fact, not that it's 45 degrees. I'm going to say that if I go counting 0 degrees north, I roll over to east, that's 90 degrees. I get down to south, that's 180. If I get to 270, then that's due west, or the negative x direction. So I need 45 less than 270. So if I take 40 from 270, I get 230. So this would be 225. So I'm going to say it's 200. Whoa, Nelly. I'm going to say it's at compass heading of 225.00 degrees. And then I'm going to say D is going to be equal to, in this case, maybe I will say it is 10.00 meters at, let's say, negative 36.87 degrees. Now I've shown all the vectors in all the possible ways. Now let me go back and show you on a coordinate system what we sort of need to understand. So I'm going to draw a coordinate system right here. Okay. Now there's a lot of things going on here. This is my x-axis, but it also happens to be east, and it also happens to be a compass heading of 90 degrees. This is my y-axis, but it also happens to be north, and it also happens to be a compass heading of 0 degrees or 360 degrees. This is south, but it's also 180-degree compass heading. This is west, and it's also 270-degree compass heading. So that's what you need to understand to be able to use all those. And when I say something is west of north, then I mean you're going to take and go from the north axis and go to the west. So that's west of north. And if I say it's south of west, then that means like this, and I'd call this S of W. Whereas this would be W of south. And this would be south of east. And of course, you could also do this one. Can anybody guess what this one would be? I'm going to make it red to stand out. Anybody guess what that would be?
East of south.
Exactly. So, does that make sense to everyone? All right, so let's go ahead and begin with this. Basically, I've tried to put a vector in each coordinate in each quadrant because that's the key. Is you got to understand how you decide what the vectors are in each case. So I'm going to draw me a coordinate system again, and I'm going to try to draw it sort of in the middle of the page that I have here. Okay, and this is my x-axis, obviously. And this is my y-axis, okay? So my job is to try to make this vector as scalable as possible. So I'm going to go on the idea of this first one being 53.18 degrees upward. So one way I know I can do that is going to the right 3 and then up 4. So I know I need to go from the origin to this dot right here, and that I need it to be something like 15 meters. So what I will do here is I can't fit 15 centimeters here, but I could in principle fit, let's say, 3 centimeters. So now I'm going to lay a protractor. Ooh, Nelly. There's lots of problems associated with laying protractors down on my good notes. I'm going to now try it with paper in hopes that that works a little better. So I know the actual, ah, darn it, where did my dot just disappeared? There it is. Okay. So now I'm going here again, and I'm trying to line it up just perfectly. So I went right through the right spot. Now I've got to actually make that into what I called 3 centimeters. I guess I could do 7.5. That wouldn't be too bad, but then that 21 would bite me. So I'm going to go with 3 centimeters. And using my protractor as a scale, I'm going to say that the 3 ends right there. Oops, there it goes again. There it goes again. Right about there. Let me check and see how this looks because it's getting really problematic. It's actually should be about right here. Dang it. I don't know why it keeps doing this, but it's being a jerk. Ugh. Why is it doing this? Y'all don't see it from your side. It's a nightmare. Okay. It's putting up all sorts of crazy boxes. It's doing everything it can to refuse to write what I want. So I'm gonna have to figure out on the fly what 3 centimeters is and use that real quick. So hold on just a second. I'm gonna write 3 centimeters on this piece of paper and then use the paper. Which obviously brings in a lot more error, but I can now see I'm using paper to lay it on this vector, and then I've got a mark on it at 3 centimeter mark. So I'm hoping that I can now use that to mark the actual spot where the vector needs to be ended. That is not helpful at all. Why is it doing this to me? And all my tools are gone. I gotta remember how to get them back here. Nope, that's not good. All right, anybody remember how to get my tools back? Okay, there they are. So now what I'm going to do is I'm going to just use the eraser to erase all but the last 3 centimeters in case that actually works. So I'm putting this 3 here. Whoop, I went too far already. But I can continue it and just go right to there. Okay, that's pretty good. So what I'm going to do is when I draw my vectors, I usually just do something like that. And that way I know where the head is. And that's vector A. Sorry about it taking so much time. Now what I've got to do is imagine another coordinate system here. This one I'm drawing west of north. So really all I need is the y-axis, which should be, of course, parallel to these graph paper lines. So I'm going to attempt to draw an axis parallel to that graph paper line, and that's what I did. Now I'm going to use my protractor to try to get 30 degrees. I have to use a protractor here because there's not an even number of integer dots we could use. So I'm going to say 30 degrees west of north. I'm putting the center of the protractor right at the very end of the first vector, and I'm making sure the line that goes from the center of the protractor to 0 degrees, I'm making sure that that actually points straight along the red line that's representing our y-axis. Now I'm going up to, since it's 30 degrees west of north, I'm going up to 30 degrees, which would be way up there. Now, hopefully I don't have to draw it that far, but the main thing is I can if I want to. Uh, I just have to now scale it back, and I need to write down what that scale was, which was specifically 3 centimeters is equal to 15 meters in reality. So my scale was 3 centimeters equals 15 meters. Okay. Now I need 20 meters. Whoa, no. Now I need 20 meters. And obviously, I could multiply 5 by, what, 4/3? Because a third of 15 is 5. And yeah, so 4/3, which would mean this would be 4 centimeters. So now instead of 3 centimeters, I'm going to make another mark on my little piece of paper that I can use to mark distance. And this time it's going to be 4 centimeters instead of 3. So doing this very carefully, okay, I can now mark off that my vector is well into the worded area. So that kind of bums me out, but it's okay. I can deal with it. What I'm going to do is try to again pull out my eraser and try to keep an eye out of where the erasing should happen. And that is not it. That was way too far. So what I'm going to do is let's try to move this whole diagram down. Cut. Paste. I'm going to bring it over here. That's good enough. I can tell where those words came from, so I'm going to leave it right there. And I'm going to say 53. Go ahead and write this down. 53.18. Ooh, 53 point. It was actually not supposed to be 53.18. That was 36.18. So it's 53.13 if I remember correctly. But either way, the main thing is we got that. And we got B is equal to 20.00 meters. Like that. And this is meters at compass heading of 225 degrees. And that's it. So we haven't really lost anything now. What we do have is the ability now to go ahead and stretch this out to 4 centimeters, which I'm going to try to do. And again, I'm going to grab my eraser. And I just need to take a little bit off. Let's see if I got it right that time. Yes, so that's pretty good. I can erase all this stuff too because I don't really need it. Don't really need it. So that's my vector B. Ah, darn it. Saved it. So that's my vector B. Okay. Now vector C is at compass heading 225, which I know is 45 degrees below due west. So what I'm going to do is use my protractor to draw 45 degrees below west. I've got this set up where the center of my protractor is right at the end of this vector, and where my line that goes from 0 to the center and then from the center to 180 is parallel to the horizontal lines. So now I need to go over here and put an angle of 45 degrees, which is right here. So I've made that little mark. Now what I want to do is use my straight edge paper again to draw a vector through that mark, and then we'll shorten it to the appropriate size like we've been doing so far. Hopefully this all works. That actually turned out pretty good, even though I knew for a fact my pen moved just a bit. Now in this case, this one's going to be 14.14. So basically I can divide both sides by 15 of the 3 centimeters equals 15. So 3 centimeters equals 15 meters. I'm going to divide both sides by 15 meters. And then I'm going to multiply by 14.14. And 14.14. Okay. So 3 divided by 15 is 0.2. And then I multiply that by 14.14. And that gives me 2.828. So 2.828 centimeters is equal to 14.14 meters. So I need about 2.82 centimeters. I'm again going to mark this on my piece of paper and then use that to find out what it should be. Y'all pray for poor Mr. Younger. He's having a bad day. So 2.82, this is not going to be easy to do, but I can do it. And I'm looking at 2.5, I'm looking at 3. Let's do 2. I think that's about 2.82. Now I'm trying to do this as precisely as I can, but you can see I'm not being very successful at it. So if I get it right, even close, it's going to be pretty impressive. And that's what happened today, as I rarely on the board am able to get these things so close. But today I got less than 3% error and did way worse than I'm doing right now. So that's kind of good. All right, this is vector C. Okay. Now, in this case, we've now finished C, and my last job is to do the 2 or the 10 centimeters. And obviously, if I divided 15, or if I multiplied 15 by 2/3, then that would become 10. And if I multiplied 3 by 2/3, that would become 2. So I know the answer is 2 centimeters. And I think I might have even drawn a 2 centimeters already. Nope, I did not. I drew a 4 centimeters. So I know that's the next length, but I also know it's supposed to be 36.87. So what that means is 36.87 suggests that the 4 side of the triangle would be horizontal and the 3 side of the triangle would be vertical. So what I'm going to do is imagine going to the right 4 spaces, which I think you will all agree is right about here where that little dot just popped up. And now I'm going to go down 3, which would be 1, 2, 3. So I'm going to say roughly there. And that should be very, very close to uh, negative 36.87 degrees. Let me just check it to make some sense out of that. If I put it here, there it is. Ooh, I missed it by a lot. Okay, I'm definitely going to change that now. So, locating the protractor at the center, at the actual head of the vector. And now I'm trying to go to 36.87 degrees downward from horizontal and to the right. So that's going to be roughly right there. Now I'm going to use my straight edge, see how far I really was off. Actually, it wasn't too bad. This straight edge goes pretty darn close to that first dot I drew, so that doesn't upset me. And that is roughly the angle that I'm supposed to shoot at. Now, at this point, I need to mark off 2 centimeters. So again, I'm going to take my scale and my piece of paper and try to mark off 2 centimeters. Okay, I now have a mark of 2 centimeters, which thank God is really, really small. And I got to pop out my pencil again, and I'm going to put it on eraser so I can do pretty well. Okay. Well, that's nice. It's right there, but obviously I had to erase some stuff that I didn't really mean to. But that's okay. All I lost was a little bit of the y-axis. And what that means is this, darn it, is this vector is vector D. Now, remember, when you're drawing any number of vectors to be added, you draw from the tail of the first to the head of the last when they're in head to tail. So I can now draw the resultant vector as a vector that starts at the origin and ends at the head of D. So I'm setting up a piece of paper that I can use as a straight edge going through the origin like that. This vector right here is my resultant vector. And now I can use that to figure out roughly what the magnitude is. I'm using the same scale I used before. I'm putting the ruler up here, and this looks like about, let's see, that would be 1, 2, 3, 4. I'm going to call that like 2.87 centimeters. That's the length. And of course, uh, 3 centimeters corresponds to 15 meters. So 2.87, I can multiply 3 times 2.87 over 3. But then I have to do the same thing to 15. So that would make the left side 2.87. So that would make the right side 15 times 2.87 divided by 3. That gives me 14.35. Darn it. So that's the resultant's magnitude. I'm believing R magnitude is equal to 14.35. Now, you'd be surprised at this because my centimeter scale doesn't even have like tenths. It only has halves. So I'm really, swinging for the fences on this one. Now I can also measure that this angle is clearly west of north, and now I'm going to figure out what that angle is, which is not easy because the vector is too short to really show it. It looks like it's right on the money at 15 degrees, maybe 14.9. So I'm going to say this angle right here is 14.9 degrees, and I would call that west of north. So that's what I believe my resultant vector is graphically. Now, I did all this just to show you how to do it graphically. Obviously, you'd have a lot easier time if you did it on a big sheet of paper using a protractor and a very thin pencil lead mechanical pencil and a straight edge and a ruler and all that good stuff. And you should be able to get well under 5% error for any of these. So this is always a default way you can go back and check your work. But if you have access to AutoCAD, that's 100% zero error. It always will give you the right answer. So if you know how to work AutoCAD, you could actually draw that. Now I got to show you exactly how I compute the actual addition of the vectors mathematically. So I'm going to start off with vector A. Vector A has a x component right here, and it has a y component right here. Now I'm drawing them blue because they're pointing in the positive coordinate directions. So that'll remind me that they should be positive. This angle for A was 53.17. That's what I intended it to be. Just double checking over here. Yeah, 53.13. That's what it was supposed to be. Oopsie. It doesn't matter because I didn't actually measure it that precisely with the protractor. I used the 3-4-5 method, and that should do it. So we got 53.13 right there. Now, this side actually had a length that was equal to 15, which remember that normally the hypotenuse is 5, so it's all multiplied by 3. So the 4 side would be 12, so this is going to be positive 12.00 meters, and the 3 side would be 3 times 3 times 3, and 3 times 3 is 9.00. Again, it points to the right, so it's positive. So 5 times 3 is 15, so 4 times 3 is 12, and 3 times 3 is 9. So that's my two components for that one. This one, on the other hand, is 30 degrees west of north. And if you look over here, I can see that the 30-degree angle touches the square root of 3 side. Okay. And the B, by the way, had a length of 20 meters. Okay. So with that one, I'm going to draw the Y component, which is positive, this way. And then I'm going to draw the X component. I shall draw it purple because I'm going to consider that the color for a negative symbol. Okay. So this is negative and some number, and this one's going to be positive in some number. As we said, the 30 is opposite the short side. I obviously multiplied by 10, so this would be negative 10.0. So again, this is just a place where you guys would be putting in your calculator 20 meters times the sine of 30 degrees, and that should give you 10. And then 30 meter or 20 meters times the cosine of 30, and that should give you 17.32. And that is B sub y. Okay. Now in this one, C, that was the 45-degree below. So the X component and the Y component are both negative. So I'm going to draw it like that. And then like that. And of course, this side was 14.14 meters, which is 10 times the square root of 2. So, and this angle is supposed to be 45 degrees. I swear it doesn't look like 45 degrees, but I'm going to have to pretend like I trust it. And either way, what we're doing is, yeah, it's clearly not. But anyways, this one would be C sub x is equal to negative 10.00 meters, and C sub y is equal to negative 10.00 meters. That's the y component there. And then finally, all we have to do is the D. So I got to break its vectors down. The Y component is obviously negative. The X component is in fact positive. And this vector specifically had a length of 10.00 meters. And this angle right here was 36.87. So is this angle. Okay. So the 36.87 is supposed to be opposite the wait a second, am I using the right? Yeah, I am using the right one. That was 36.87 downward. That would okay. So that all worked good. So opposite the 36.87 would be the 3 side. And the 3 side, since the hypotenuse is 10, that's clearly 5 times 2. So I got to multiply 3 times 2. This side would be negative 6.00 meters, because 3 times 2 is 6. And that would be d sub y. And this side right here would be d sub x. And that one's got to be 4 times 2. So this one would be d sub x is equal to positive 8.00 meters, like that. Now, again, if you were taking this in a 201 class, it's very common for us to do a table where we'd write vector, magnitude, direction, v sub x equals v cosine theta, and v sub y equals v sine theta. And if you're strict about exactly what angles you're using, which I'm going to convert to those as we go, then you could, in some sense, use those formulas. You have to still check your signs. But let's start off with writing the vector A. That vector A had a magnitude of 15.00. I'm saying that's in meters. This is in meters, and this is in meters, and this is in degrees. Okay, now it's 15 at 30 degree, or excuse me, at 53.18 degrees, and that is measured the proper way. So I'm going to say 53.18, and then the x component of that, of course, was 9. So that's going to be 9.00, and the y component was also positive, and that one was 12.00. Now we write back vector B. Vector B had a magnitude of 20.00, and its angle was 30 degrees west of north, which is basically 120 if you measure counterclockwise from the positive x-axis. So this is 120.00 degrees. In this case, I got 17.32 for my y component and negative 10 for my x component, like that. Now vector C had 14.14 as the magnitude. Now it was at a compass heading of 225, so I can just say that is actually a standard angle that goes 180 plus 45, so that's going to be 225 as well. I don't know why I'm putting the degrees there. I already marked it. And this vector C, we found, had a negative 10 x component and a negative 10 y component. And then finally, vector D. Vector D had a magnitude of 10 meters. Are almost out of time. Don't worry, I'll knock it out. And in fact, this one's at negative 36.87. That's a standard angle. So I can just write it like that. This one had a x component that was positive 8 and a y component that was negative 6. Now, when you make this table, you then put a line right here and you put an X in here because you don't want anybody to think that they could actually add angles and magnitudes and get out angles and magnitudes. But I'm going to write R for the resultant vector here. And I'm going to say 9 plus 8. Well, 9 minus 10 would be negative 1. Minus 10 again would be negative 11. And then plus 8 would be plus 3. So I'm going to say the x component, actually, it should have been minus 3, right? 9 minus 10. Yeah, it definitely should be minus 3. Okay. The y component, however, 12 plus 17.32 would be 29.32. Minus 10 would be 19.32. Minus 6 would be 13.32. Like that. Now all I got to do is draw an x and y axis. And now I've got to do the opposite of resolving a vector into components. I've got to take components and put them together. Okay, what I have is a x component that is negative and very short. So I'm going to say that's negative 3.00. And then I got a y component that's big and positive. It should be about 4 times as big. I can't really show that well here. But the main thing is you can tell clearly the angle from the y-axis is way less than 45 degrees. In fact, this angle right here and this vector right here is the resultant vector r. And what I'm going to do is find this angle, which is the same as this angle. Okay? So r is equal to the square root of 3.00 meters squared plus 13.32 meters squared, and then take the square root. In other words, the Pythagorean theorem works. Of course, if you had 3 components, you would actually have the Pythagorean threesome squared. So in this case, I get 3 squared plus 13.32 squared. That gives me 186.42. I'm going to take the square root of that, and this gives me 13.65. That's not too terrible. I came up with 14.35. That's 13.65 meters. That's the magnitude. Now the angle, what I know is the tangent of theta, or excuse me, the tangent of phi. So the tangent of phi is opposite over adjacent. Notice I'm not putting the signs in at all. The opposite is 3, and the adjacent is 13.32. So phi should equal tangent inverse of 3 over 13.32. So I'll say 3 divided by 13.32 is equal to that. Now I'm going to just say, ooh, Nelly, I just did something really bad. I just lost. Okay, hold on. My fat fingers hit something. Okay, so now I'm going to do arctan of the answer that I just got, which was 0.225225, which is fun to find. And that gives me 12.692 degrees. So I had read 14.9 degrees west of north. We got 12.62. So what this tells us is our R vector is actually equal to 13.65 meters at 12 point, let's call it 12.7 degrees. west of north. And that is how we add vectors. Okay. Now, you might imagine if you subtract vectors, then the rule that we used last time was A minus B is equal to A plus the opposite of B. So guess what? You take the components and you multiply them by a negative. If you have it in a different notation where you don't have I, J, and K, all you're going to do is keep the magnitude the same, but you're going to add 180 to the angle, or if it's already bigger than 180, subtract 180. That would work as well. So we're good. We've done what we needed to do regarding this. I ran over 2 minutes. I apologize for taking the extra 2 minutes, but at least we got that done. And I'm going to I'm going to make sure the homework's not due this Sunday. I'm going to make sure it's due, let's say Tuesday at 11:59 p.m. Because I'm going to cover some more projectile motion stuff, specifically just projectile motion next time. But I think you're now in a good spot to have some understanding of how to add vectors. I may or may not have made some arithmetic or uh, trigonometry errors, but generally speaking, everything that was done here was pretty correct. So, or was correct physically. It just might have had some little errors around the edges. So, you guys are free to go. Make sure you chat me your first and last name before doing so. Make sure you get your tests finished this weekend. Remember, you don't want to miss a test. Also, turn in your syllabus if you haven't already. The little workout sheet at the end. I'm going to be knocking that out tomorrow. And you guys have a wonderful weekend. And thank you for coming, and I will see you next time.
Thank you. Have a good night.
You too. Thanks, Brianna. I'll wait for the last person to leave in case anybody has any questions, like always, of course.
Hey, I just had a question about the homework that was graded, the lab.
Okay.
Um, I noticed I got 5 off for it says for not reading my meter stick into two decimal places, but I did on the lab. So I was wondering if I missed something there.
So normally what happens is if you have two decimal places, uh, then each of those numbers will be different. So a lot of times, if someone has five double zeros in a row, or even five zeros in a row in the last digit, then that seems almost obvious that they didn't really measure it to two decimal places. They just put an extra zero on it to make it look like that. I'm not saying that's what you did. Oh, why did the screen just go blank? But what I am saying is that that is one of the indicators. Another thing, another reason I would do there. Are you still there? Because
I'm still here. Yeah.
okay. Okay. Another thing that will happen is like you'll have 13.0 instead of 13.02 or something like
Hmm.
that. So if you have any of those that only have one decimal place, that's what it's for. And usually what I do with the first lab is if there's a lot of grades that are, below 90, I will sometimes let people correct the error, turn it back in, and I give them maybe not to the full 100, maybe I'll give them back up to a 95. So I might do that with you with this class, but just know I tried to mark off every little thing, even if you only did it once, just so you'd know the rules.
Oh, okay. Gotcha.
Okay. Yeah, so when you're using a meter stick or anything that's marked with 10 spaces between 1 centimeter and 2 centimeters, anything like that, you can get two decimal places, unless it's something really weird that you're measuring that's not very square, or you have to measure off over a space that you can't actually get the ruler right next to the thing. That can sometimes be a good reason not to have two decimal places, but other than that, it should have.
Right. Yeah, I had 9 out of my 10 measurements all had two decimal places, but I think I had a little bit of a typo with one of them, so that's probably what you were trying to hit.
Gotcha. Yeah, another thing I took off for is some people didn't follow the instructions about zero point 0.6 and zero point 0.7 seconds on the dropping of the ball, and that sometimes is a problem.
Hmm.
So, is that all
Okay.
you had marked off, Chloe?
That one, and then I taking the L on the sig figs one because I see where I made a mistake on that.
Gotcha.
All
Yep.
right.
If you got in the area of a 90 or higher, you did really well. An 85 is not bad either, though. So I don't know what you got, but I just let you know.
All right. Thank you.
All right. See you, Chloe. How
Bye.
about you, Aiden? You got a question? I don't know that Aiden's here. You can type it if you don't have a speaker that works, Aiden. Okay, I think he's not here then. All right, everyone. Thank you for coming. Bye bye.